Mr. Causey here. Now, if you want to know about the game of Sprouts and you don't already know about it, please click on the link below, which is my first video on Sprouts, and it explains how the game is played. So, to give context to the first question we're going to investigate about Sprouts, let's first watch a typical game unfold. Now, this one starts with 4 dots, and we concentrate on the total number of moves made in the game. So there's the last legal move, red wins, that's move 10. So this particular 4-dot game of Sprouts had 10 moves. Now, could it have had 11 moves? Would it have been possible to have 12 moves? Or could a Sprouts game go on forever? Well, that's the question we're now going to investigate. And we're going to do that by examining a concept called the lives left of a dot. So we'll look at a typical dot, a dot that has no lines coming out of it. Well, it has 3 lives. A dot with 1 line coming out of it has 2 lives left. A dot with 2 lines coming out of it has 1 life left. It's room for 1 more line. And a dot with 3 lines is dead. It has no lives. So there's a dead dot. All the other dots in a game that have 3, 2 or 1 life are live dots. Remember, all dots must be either alive or dead in a game. So let's examine the initial position when we have a 4-dot game like the one we illustrated there. So we start with 4 dots, all of which have 3 lives. So there's 4 lots of 3 lives in the initial start of this game. So 12 lives to begin. And likewise, if we generalise towards an n-dot game, if we start with n dots, and we've not moved, so there are no lines in there, there'll be n lots of 3 lives available for lines. So we start with 3n lives. Now, we must consider then, if we make a move in the game, how does that affect the existing number of lives at that stage in the game? So what effect does 1 move have on the total number of lives? So let's look at a typical move. We'll start with 2 dots. A line out will remove a life, and a line in will remove a life. But the new dot has 2 lives removed anyway, but there's a new room for a new line there. So overall, 1 life has been removed. And a loop, similarly, there's 2 lives removed, 1 added. So overall, there'll be 1 less life. So we've found out that during the course of a game, each move that's made will reduce the number of available lives in that game by 1. So armed with this analysis we've just done, let's work our way through a typical 4-dot game like the one we've got on the right there. And we'll look at lives and move numbers. So let's make up a table. First of all, with our move number, and let's track the number of lives that are left. Now, we know that in a 4-dot game there are 12 lives initially, so if no moves have been made, 12 lives are left. When 1 move is made, 1 life is lost, so there's 11 lives left. On move 2, after move 2, there will be 10 lives left, and after move 3, there will be 9 lives left. Now you notice they add up to 12, each of these pairs of numbers. So we can continue that on. Suppose we had 12 moves, there would be no lives left. 11 moves, there would be 1 life left. 10 moves, like the one we have here, 2 lives left. What's this analysis telling us? Well, let's look at move 10 in the analysis. Move 10 tells us that we're left with a situation where overall there are 2 lives left. Now, if you look at the game that's been completed on the right, here you can see 2 dots, each of which have 1 life left. Now, what our analysis is attempting to do is to find the theoretical maximum number of moves. So a game could be played where these 2 remaining dots are playable, and we can join the 2 dots with a line, and in that case we could make a move 11, which would leave us with 1 remaining life. Now, having 1 remaining life, it's not possible to complete another move at all. You need at least 2 lives to produce a valid move. 11 moves would be the maximum number of moves possible. Move 11 is the last possible move. So the maximum theoretical number of moves in a 4-dot game of Sprouts is 11. That's 1 less than the 12, 3 times the number of dots. So let's now move on to an analysis, similar analysis, in an n-dot game, where we'll make up the same type of table, where we show the number of moves and follow the number of moves through and see how the number of lives pans out. So again, if there's no moves having taken place, we know there's 3n lives available in all the dots. 1 move later, there'll be 1 less life, 3n minus 1. 2 moves later, 3n minus 2, and so on. And again, these add up, in this case, to 3n, the pairs of numbers. So if we followed this through to the end of the table, we can see that 3n, move 3n, would have left 0 lives. Move 3n minus 1 would leave 1 life, and move 3n minus 2 would leave 2 lives. And of course, if there's 1 life left, there are no further moves. So the last move possible, maximum number of moves, last move possible is move 3n minus 1. So again, in this case, we can make the analysis that the maximum possible number of moves in an n-dot Sprout game is 3n minus 1. So we're now going to consider whether there's a minimum number of moves possible. For the 10 moves in the 4-dot game, could it be 9 or could it have been 8? So let's consider a completed game using n dots. So it starts with initial dots n. We'll suppose that the number of moves is m. And at the end of the day, there's going to be a few live dots and the rest are going to be dead. We'll call the live dots survivors. In this game there's 2. And the rest of them are dead. Now the dead dots can be divided into 2 groups. Ones that are right next door to survivors. We'll call these ones guards. So guards are neighbours of survivors. So there's the 2 survivors in that game, and there should be 4 guards in total. So there's the 4 guards, 2 for each of these survivors. And we'll call the number of guards G. Now the rest of the dead dots that are not guards, Conway called these Pharisees, and the number of Pharisees, will use the Greek letter phi for them. Now I want to look at the concept of a guard in slightly more detail, because it's a subtle one. Remember, a guard is a dead spot that's a neighbour of a survivor. or one of the surviving live dots. So suppose this is a survivor. Now necessarily a survivor must have only one life left. If it had 2 lives, for instance, you could have looped and another move would have been possible. And we're now analysing a completed game where no more moves are possible. So a survivor has 1 life. Now a survivor in this case, the dots that these lines go to, neither of these can be live, otherwise another move would have been possible. So both of these dots must be dead. So there's a survivor, and there are the 2 guards. Now that's not the only situation we can have. Suppose a survivor is a survivor on a loop. Now obviously that dot here cannot be live, otherwise a further move would be possible, so it must be dead. However, the dot that this line goes to also cannot be live, otherwise another move would have been possible, so this must be a dead dot, and it's also considered to be a guard to this survivor. Now, looking at these diagrams, each survivor has 2 guards. Now, there arises the possibility that one of these guards, for instance this one, might be a guard of a completely different survivor. Now, that's not possible. You can attempt to make that diagram and you'll discover that every time you do that, the other survivor, you'd get an extra move that was therefore possible. So it is true that each survivor comes with exactly 2 guards. So let's now attempt to gather a lot of these ideas together. So we're looking at a completed game that we started off with n dots. Now each move in this game will produce a new dot. So by the end of the game, because there was m moves, there'll be n plus m dots. And we've discovered that some of them are alive, that's the survivors, and the rest of them are dead. And we've also established that the dead dots at the end of the game are of 2 types. They're the guards, there's G of them, and there's the Pharisees, phi of them. And remember that each survivor has 2 guards attached to it. So the number of guards must be twice the number of survivors. So here's progress. Now the other idea we came across, certainly in the first half of the video, was lives of dots. So if we examine the remaining lives in this completed game, now remember when we start off with n dots, there's 3n lives. Each dot has 3 lives. A move removes 1 life, and there were m moves, so we're ending up at the end of the game with 3n minus m lives. And where the lives are, each survivor is associated with 1 life. So 3n minus m must be the same as the number of survivors. So we can certainly substitute this s for 3n minus m. So let's do that. And let's simplify this as far as it will go. That will give us 9n minus 3m plus phi. Now, m plus 3m on the left. Let's take n's onto the right hand side. It'll be 8n and plus phi. And so we end up with what Conway cleverly called the Moribundity equation. He had a way with words, did Conway. A moribundity equation. And the easiest way of stating it is if we divide through by 4, number of moves will be twice the number of dots you start with, plus a quarter of the number of Pharisees. Now what does this mean? Suppose we've got a game where the number of Pharisees is none. Then the number of moves would have been twice the number of initial dots. And you can see also from this that the number of Pharisees must be a multiple of 4, otherwise the number of moves would not be an integer. So the next value if I could take would be 4, in which case the number of moves would be 2n plus 1. And so it goes on. In the case that we've got over on the right here, the number of Pharisees is 8, and therefore the number of moves is 2n plus 2. And remember, in the example game, we started with 4 dots. 2 4s are 8, plus 2 is 10, and certainly the number of moves was 10. So that's all fitting in with this example that we gave. However, what this is showing is that the minimum number of moves is 2n. So the number of moves must be greater than or equal to 2n. And remember, in the first part of the video we said that m must be less than or equal to 3n minus 1. So overall we've got the number of moves possible in a game of Sprouts jammed between twice the number of dots and 3 times the number of dots minus 1. So now that we've established a lower bound and an upper bound for the number of moves in a Sprout game, let's see what that means in the case of small numbers of dots. So let's start with 1 dot. So n equals 1. Now this inequality then becomes 2 less than or equal to m less than or equal to 2 again. So in a 1 dot game, this is telling us there can only be 2 moves. Well, let's see how this pans out. Let's go to the first player moving. Blue leads. So only one choice for the first player, and that's to do a loop. Now the second player, red, responds, and now there are only 2 live dots. So the second player, red, can only respond in that way, adding a dot. And now there is no play for the first player. So the first player loses in this case, second player wins. Let's have a look at 2 dots, a 2 dot Sprouts game. And that inequality tells us 4 less than or equal to m less than or equal to 5. So all 2 dot Sprout games must have either 4 or 5 moves in them. Now it's not at all obvious that that's the case. In fact, this becomes quite a complicated analysis, as you can see from this diagram. So we're looking at 2 dots. Now the first player has 2 basic choices. They could either just join the 2 dots and put another dot in the middle, or loop on one of the dots and put a dot on that loop. There are essentially no other types of moves. So the first player has 2 choices. The second player then has to respond to that. And as you can see in this diagram, there are 3 distinct possible responses to this blue move, and there are 4 distinct possibilities for responses to this blue move, this first move. And if we follow the tree down, red would have to respond in a way that always allows only 4 moves as a possible end to the game. Otherwise, if there's a 5th move, blue would then win. The first player would then win. So it's the second player's aim is to get only 4 moves possible in this game. Well, I suppose the first player's aim is to end the game with 5 moves. Now, there is therefore a strategy. You can see it in here. So if you're playing a 2-dot game of Sprouts and the first player just joins the 2 dots like this, your response is to complete, if you like, a circle. The 2 live dots there at the ends should be joined. So your response, should the first player do this, is to join the 2 dots at the end to produce, if you like, a circle. Now remember, this is a topological game, so you can move lines, bend lines, so long as you don't cross other lines. They can be bent and moved around, so long as they're not chopped off or cross other lines. So you should end up with a game like this. Now your response to that depends on what the first player then does. First player could draw a dot inside that loop, in which case your response, there'd only be 1 to join the inside dot to one of the live outside dots. And then blue has no response to that and red wins. Or the other way that blue could have responded to this loop is to, in effect, join 2 outside dots. And if that's the case, your response to that would be, as you can see in this, is to create, instead of joining these 2 live dots outside, you would stay inside, join the 2 live dots that are side by side inside the big loop. And that's what appears there. And then blue has no response to that. However, if blue starts off by looping on one of the dots, then your response immediately is to join the 2 live dots of that loop inside, and therefore put this extra live dot inside that loop, and that seals it off in effect. And that means blue has only one choice. Blue has to loop on that 1 remaining dot, and your response, you have 2. You can either join the 2 active dots inside that loop or join them on the outside. In either case, blue has no response for that, and you as the second player would win. So what this tree is showing you is that if there's a 2-dot game, then the second player has a winning strategy if they play the best choices. And that we also found for 1-dot Sprouts game, the second player has a winning strategy. So continuing in this way, we can see that if n was 3, a 3-dot Sprout game would have lower bound 6 and upper bound 8. A 4-dot game, that's the sample game we gave earlier in the video, lower bound would be 8 and upper bound is 11. In a 5-dot Sprout game, lower bound is 10, upper bound is 14. And so it goes on. And you can imagine the tree diagrams for these get extremely complicated, and they do, but they have been analysed up to a certain number of dots to find if there's a pattern in who has the winning strategy in a game. So that's the question that we'll start investigating now. Question, which player has a winning strategy? Now here's a table showing the number of dots in the game, and we'll fill this in with a blue dot if the first player has a winning strategy and a red dot if the second player has a winning strategy. Now when there was 1 dot, the first player goes and the second player then wins. There's no choice. So there is definitely a winning strategy for the second player in a 1 dot Sprouts game. 2 dots, we had a look at the big table and we decided that if they play their best move, the second player always has a winning strategy. Now remember that Sprouts was invented in February 1967 by John Conway, professor at Cambridge University, and Mike Paterson, a graduate student. And it was not long after they invented the game that Conway showed that definitely in a 3 dot Sprouts game, the first player has a winning strategy. Now it was at this point that Denis Mollison took over this research. And at the time he was a mathematics student at Cambridge and he investigated the 4, 5 and 6 dot games. And very quickly he showed that the 4 and 5 dot games have a winning strategy for the first player. The case of 6 dots is interesting. Conway believed that Mollison couldn't analyse it, it was too complicated. So he challenged him to do it within a month, a 10 shillings bet, and Mollison proceeded to win the bet and analysed it by hand, 49 pages of diagrams, and his discovery was that the second player had a winning strategy in a 6 dot Sprouts game. There was then a gap of 23 years before any more progress was made at this question. And in 1990, there was a group at Carnegie Mellon University who used a computer to analyse all the games starting with 7 dots up to 11 dots. Their names were David Applegate, Guy Jacobson and Daniel Slater. Now their analysis of these games was quite interesting. They discovered that a 7 dot Sprouts game was won by the second player, as was the 8 dot Sprouts game. And then when the 9 dot Sprouts game was analysed, it was back to the first player, as was a 10 dot game. Now can you predict the 11 dot? You're right, it's a first player winning strategy game. This led to what's known as the Sprouts Conjecture, that the first player always has a winning strategy if and only if the number of dots n is congruent to 3, 4 or 5 mod 6. All that means is you take the number of dots, divide it by 6, look at the remainder. And if that remainder is 3, 4 or 5, the first player has a winning strategy. If that remainder is 0, 1 or 2, the second player has a winning strategy. So the conjecture is stating that the pattern 3 blues, 3 reds, 3 blues continues indefinitely. Now, interestingly, if there was a game with no dots, you could argue that the first player cannot play and therefore the second player wins. And therefore in the no dots Sprout game there's a winning strategy for the second player. In which case we would have 3 reds, 3 blues, 3 reds, 3 blues, etc. Some progress has been made in this question since 1990. 2006, the cases 12 up to 14 were established and they fit the conjecture. 2007, a lot of results came out, all fitted with the conjecture. 2010, the same group increased our knowledge. And then finally, in 2011, they added a few more results. Now, if you look through all these and summarise them, basically the cases that now are known, up to 44, with 46, 47 and 53 dots, all of these cases fit the conjecture. However, to date, the conjecture remains unproven. No amount of checking individual cases can prove a conjecture, so that still remains to be proved. So that's Mr. Corsi signing out, and I hope you enjoyed the video.